Okay, in the next, we're going to talk about a very interesting topic called the random incidence phenomenon. Here's an example of the problem that we are interested in. Suppose that we want to survey how available are the town buses in a city. We can think about probably the two ways of surveying it. The first method is as follows. First, we select a few buses at random because we cannot investigate all the buses, and then calculate the average number of riders in the selected bus. But we can think about the other method. What we can do is to select a few bus riders first at random, not the buses, and then look at the buses that they rode, and then to calculate the average number of riders in those buses. So the difference between these two methods are whether we first select a few buses at random or we select a few bus riders at random. It appears that these two methods can be possible, but obviously just one of the methods would be more accurate. So the question is, which is correct? Well, in relation to these questions, you may be wondering about the numbers that can be investigated by these two methods would be same, or maybe the M1 is larger than M2, or the M2 will be the larger than M1. So probably, one of the three possibilities would be correct. What do you think? So this is a very interesting question. And this question actually arises in our life very often, right? This problem is a sampling problem, right? We cannot count all the town buses in this example. What we can do is that we just sample in order to use that number to represent the availability of the town buses. But the question is, what is the correct sampling method? So we're going to talk about this issue. And you may be wondering, what is the relation of this question to the topic that we have studied so far, like Bernoulli process or the Poisson processes and so on. So we're going to talk about that. Okay, good. So I hope that you are well motivated by the question using this example. So let's first start from the thing that we know. In the Poisson process with the parameter lambda, and we know that the inter-arrival time is an exponential random variable with the parameter lambda. That's what we know, and that was the very important basic fact. Now what we're doing is this. We fix a time instant t star, that's a fixed time, some time. And what we are doing is that we consider the length, which we denote by L, of the inter-arrival interval that contains t star. So what we mean by that, if we understand this question in a practical context, and that is this. So Jung shows up at some bus station as some arbitrary fixed time t star, like 9 a.m. for example. That's the t star. And then what he wants to do is that he records the time from the previous bus arrival, and that is denoted by the U. Well, maybe we can do this by asking some questions to people around there. So I just show up at 9 a.m. at some bus station and then ask question to the people, when was the previous bus arrival? Well, Jung is told that there was like 8:40 a.m. for example, and that is U. And then Jung will record the next bus arrival because he arrived at the bus station at the 9 a.m. and then he just waits. And then next bus arrival is 9:15, for example, and that is V. Okay, and then he calculates the difference between the next bus arrival, that's 9:15, and the previous bus arrival, that's 8:40. And the difference between those two things are denoted by L. And obviously L is a random variable because the U is a random variable and the V is a random variable. So the question is that what is the distribution of L Now, before we go to the answer of this question, why don't you pause the video and come up with your answer, your version of answer. Okay? And then we're going to talk about the more details later. So think about that. Very good. So what is your answer? Well, the first answer that a lot of people can choose is that this L is nothing but just the V minus U, right? And the V minus U is, by definition, is the inter-arrival time. And as we have talked about in the previous lectures, well, in the Poisson process, the inter-arrival time is exponential random variable, so distribution of this L is exponential. Well, if that's the answer, then I will not talk about all these things as a special name called the random incidence. Okay, so that's not the answer, and we're gonna talk about why that is not the answer. But before we go to the main story, this question is called the random incidence phenomenon, and that's the kind of the word that everybody was using in this community. But this word is a little bit confusing and misleading, because here in this case the T star is not random. We fixed the T star like 9 a.m. So T star is not random. So the random incidence, you know, it's a confusing and misleading, but this word has been used for a long time. So that's how what the people call this phenomenon. So whenever we talk about like random incidence phenomenon, then you need to think about this question, okay? And there are many cases the people are using the words in a confusing manner. Okay, so forget about the word. So this is called the random incidence. But going back to our original question, in order to talk about the answer of these questions, we're gonna make some assumptions to make the story simple. So for simplicity, we're gonna assume that this T star is large enough so that we must have an arrival before T star, meaning that this Poisson process started long time ago, and then the T star is chosen so that we must have a previous arrival U. So, which means that the U is not 0. I mean, it's possible that there are no arrivals up to this period, so U can be 0, right? Like U can be here. So we have a U which is positive, which means that we must have a previous arrival, okay? Because if the U is 0, now mathematically it's tricky, okay? All right. So U is positive in order to make the story simple, because that's the assumption in order to simplify our discussion. So again, one might superficially argue that my answer is exponential random variable, okay, because the V minus U is an inter-arrival time, okay, and that is exponential random variable that we know. So that the answer may be the exponential random variable with the lambda, but actually it's not. So we're gonna talk about why it's not, okay. And then in order to talk about the distribution of L, then we're gonna divide into the two intervals, because this is a T star. So the L is the summation of the T star minus U and the V minus T star. So we're gonna divide it here. Oh, by the way, there would be some students who are asking the question, Professor, the mathematically L is V minus U. And we have already proved that the V minus U is by definition is inter-arrival time of 2 arrivals. So it should be the exponential random variable. I didn't do wrong. I just followed the mathematics, and then there was the exponential random variable because it's just a V minus U. Well, that's the subtle point. The subtle point is what? We have an extra condition that the T star, which is chosen beforehand, which is fixed, should be placed between V minus U. That's additional condition that we have. It's not just the V minus U. V minus U with the condition that T star should be in between the v and the u. That's the additional condition. That will change the mathematics. That's the difference. Because that was a problem. All right. Going back to our story, again, the L is divided into two intervals, t star minus u and the v minus t star. Okay. Now, v minus t star. So what is this? So if you think about that, there's a t star. And what is the length of this guy? This is from the t star, and what is the length up to the next arrival. And we know that from the property of the memoryless and the fresh restart of the Poisson process, whatever the t star is, the v minus t star is exponential random variable because it's a memoryless. It doesn't matter what happens before t star. All we have to do is to weight additional exponential random variable with the lambda, and that's what we know from the basic property of the Poisson process. Okay, so v minus t star is a exponential random variable with the parameter lambda. What about the t star minus u? Well, the t star minus u is this length, and that is how can we mathematically study that? So what we are going to do is that we're gonna do a little bit of a trick. Then we run the Poisson process in the backward time, which means that suppose that the Poisson process is this is a timeline, and we have arrival here, arrival here, arrival here, arrival, and arrival, and then this is how the time goes. But we're gonna look at this Poisson process is in a backward time, and then what happens? Well, if you would look at the Poisson process in backward time, that is also Poisson process. And why is that? Because if you think about the definition of the Poisson process, well, what was the definition of the Poisson process? Well, we have an independent number of arrivals over different time interval, and then over a very short time interval, we have only one arrival, and things like that. If you think about the definition of the Poisson process, okay? If you will look at the Poisson process is in a backward time, then for example, like, oh, let's regard this is the first arrival, and what is the next arrival? That's an exponential time, and that's an exponential time, and the number of arrivals over a different time interval, that should be also independent, and things like that. So we followed all the definition of the Poisson process. So backward investigation of the Poisson process is also Poisson process, which means that suppose that we have a t star here, and then we will look at the Poisson process in this direction, and the question is that from the t star, what is the next arrival? Here in this case, next arrival is the previous arrival. I'm talking about the u. Okay, that is also exponential, because in a backward looking at the Poisson process is also Poisson process. Well, Professor, I understand what you're saying, but I want to be more convinced by the math. Okay, so let me show you the math. Okay, more formally, mathematics says that I'm interested in the distribution of the t star minus u. So let's look at that distribution, because this t star minus u is a random variable. So I'm going to look at the CCDF. Well, the looking at the CDF and is equal to the looking at the CCDF. Okay, so CCDF, which is the probability that the t star minus u is larger than x, and that means that there are probability that there are no arrivals over this time interval. Agree? Yeah, right. Because the t star minus u we have is larger than x, then there was no arrival from the t star minus x and the t star. We have no arrivals over this time interval, and that is equal to the probability that t star minus u is larger than x, because the u was defined as the previous arrival before t star. Okay, now because this is the Poisson process and this is the time interval of length x, And from the definition of the Poisson process, that is there are no arrivals over the time interval x. And that is equal to the e to the minus lambda x from the definition of the Poisson process. And that is also equal to the inter-arrival time is larger than x. I mean, the inter-arrival means the inter-arrival of the Poisson process, right? So because this, the CCDF of the exponential random variable, this guy, is equal to the e to the minus lambda x, because this guy is the exponential random variable with the lambda. I'm just telling you that this time t star minus u, it has a distribution which is equal to the exponential random variable with the parameter lambda. And that is a mathematical verification of looking at backward of the Poisson process is also a Poisson process. But anyway, the conclusion is that t star minus u is also exponential random variable. So this guy is an exponential random variable with the lambda, and this guy is exponential random variable with the lambda. That's why we can conclude that the L is the summation of two exponential random variable with the lambda, not just one exponential random variable. And we know how the L is distributed, right? In the Poisson process, summation of the two exponential random variable, that is equal to the what? Time until we have two arrivals. And we have already studied this time until we have a k arrivals in the Poisson process, and that has that follows the along random variable with the two arrivals with the parameter 2 comma lambda. Remember the along, so along random variable is a general version of the exponential random variable. Generally, the arrival time until we have a k arrivals is the along with the parameter k comma lambda. But here in this case, we have a 2 comma lambda. So if you go back to how the along random variable has the PDF, then it has this PDF. So this is the PDF of the L. Now, what is the expectation? Well, along k comma lambda has the mean, the k over lambda. So here in this case, 2 over lambda. It's exactly the double of the mean of the exponential random variable, because it's the summation of two exponential random variables. The conclusion is that it's actually the 2 times of the mean exponential random variable, mean arrival time. So this is the main reason. An observer, so what is the question? L is v minus u, but we have an additional condition that the t star should be placed between the u and v. And what is t star? T star is the time that the observer looks at the system. So we have an additional condition that I need to be able to look at the system between the u and v. That's the additional condition, which means that observer who arrives at an arbitrary time, here in this case t star, fixed time, is more likely to fall in a large rather than a small inter-arrival time. Which means that suppose that t star is some like arbitrary time that I look at the system. It's a sampling time. If we fix the sampling time, obviously it's more likely to for a larger inter-arrival interval rather than the small arrival interval, which means that out of many inter-arrival interval, I only sample the inter-arrival interval that has larger than the mean inter-arrival interval. That's the main reason. And if we take a summation of all those inter-arrival intervals that I look at the system, because of this condition, I tend to select larger interval. That's why we have the 2 times of the mean arrival time, because my sampling method is doing like that. And that's why we get this. And that is a random incidence phenomenon. Take some time to think about this region makes sense. Okay. Going back to the problem of survey of utilization of the town buses. If you think about it, this M1 and M2, which method would be more correct in order to investigate the availability of the town buses in a more objective manner? Well, the conclusion is that M2 is larger than M1. Why is that? Because if we select riders at random first, then obviously it's more likely to select a bus, because we select the riders at random first with a large number of riders than a bus that is near empty, right? Because we select the riders first and then follow the riders and look at the number of riders in that bus. Then obviously we have higher chance to select a bus that has more passengers. So more correct method would be the M1. Select a few buses at random first and then calculate the average number of riders. Okay, so the sampling method is very, very important in order to come up with the answer that we are asking in a more accurate manner. So this random incidence phenomenon tells us the importance of how we sample the system in order to investigate what's happening inside the system. Thank you.